Hello and welcome. My name is Nick Brimley, and I am the Marketing Director of the Slag Cement Association. I will be moderating today's webinar, Slag Cement and its Benefits to Reduce Embodied Carbon in Concrete. Our speaker today is Ryan Cialdella. Ryan is the Executive Vice President of Innovation and Market Development at Ozinga, where he is responsible for exploring innovative materials and technologies to help them stay at the forefront of the building materials industry. Throughout his 20 years at Ozinga, Ryan has held various roles throughout the company's ready-mix concrete operation, making him integral to the company's continued dedication to be an industry leader. If you have any questions during the webinar, we ask all attendees to please use the Q&A feature, and we'll get to your questions at the end. And with that, I will now hand it off to you, Ryan.
Sounds good. Thanks, Nick, for the introduction. Can everybody see the screen okay?
Yes, we can see your screen.
Okay. Sounds good. Well, thanks for having me today. I appreciate the opportunity. As Nick said, I've been with Ozinga now for about 20 years, and really the last couple of years really been focusing on our decarbonization efforts throughout our whole process, from the sourcing of our materials to the way we transport them to how we actually make them in the plant. So with that, I'll dive into the presentation. So kind of just a high-level overview of what we're going to cover. Obviously, current design proportions. How are we designing mixes now? What are some of the limitations that we are up against in the industry? And then kind of taking it a step further and looking at mixes with higher slag replacement rates and some of the performance benefits there. And then transitioning over to the carbon reduction, right? What does slag offer in terms of the global warming potential that can be identified in an environmental product declaration? And then looking at some at-scale projects, not only pilots, but larger scale applications, and where we use slag in some, higher than average rates, something that, maybe is a little bit above the norm of what everybody is used to. And how does that impact carbon savings and a carbon budget for a particular project that might have carbon reduction goals? So really, where do we start, right? I mean, obviously, ACI 211 provides a guide to proportioning concrete for normal weight and high density concrete. That's always a good baseline. Again, nothing beats experience, right? Past experience with mix designs that we're used to using, whether it's, 10% slag, 20% slag, 30% slag, wherever it may be, understanding the performance implications of that, the finishability, workability, strength gain, things like that. Some do have, more restrictive applications, whether it's for ASR, alkali silica mitigation and or sulfate attack. So you may have some very strict proportions that you may need to abide by there to meet those requirements. And then again, proportioning to reduce embodied carbon, right? What if I take a mix that's got 10% slag and put in 30, 40, 50%? How does that affect the global warming potential and, for a specific application? And it may not be for all mix applications, right? I mean, there may be specific applications where it makes more sense to take advantage of a higher reduction than others. So we'll dive into that a little bit more later. And then it just increased durability. As we know, increasing levels of SCMs, whether it be fly ash and or slag, or in combination with each other, do provide some durability benefits for the total life cycle of the concrete itself. So what can't you do, right? I mean, really, the main limitation that we all come across is, ACI 318, for an F3 exposure class when you're exposed to de-icing salts and freeze-thaw environments. It does limit slag to 50%, and, other pozzolans, such as fly ash, to 25, or in combination of each other, 35 or 50%. So, that is one restriction right now that we do face in specifications. And, with some understanding why to a degree, but I think there's some opportunity as the carbon reduction movement continues to move forward to really start to understand what are some other steps or other measures that we can take where we might be able to go to 50% or 60 in an application like that. So I think there's some room for looking at that and figuring out how do we do a little bit better, and how do we help, not only get the carbon reduction we want, but get the long-term durability in why people do design with concrete in terms of its whole life cycle and low maintenance and low cost that way. So one of the other restrictions is obviously DOT type work. There's a lot of that work coming up, obviously with the IRA funding and things like that. So looking at states and their max replacement rates when it comes to slag cement, as you can see, vary from 50% to no max to 30% in some spots. So really understanding kind of where your limitations are at and figuring out what is that, how does that affect me in the mix designs that we produce based on these restrictive prescriptions. Obviously, there's quite the movement to move towards more performance based, and so we really took that to heart a little bit, and within our own lab, thought we'd push the boundaries a little bit, right? Let's take a look at a mix design and go over that 50%. Look at the baseline, look at the 50%, and figure out how do we understand what are the implications of going above that. So obviously our biggest footprint here is in the state of Illinois. So we kind of looked at the IDOT spec, and when it comes to performance reductions slag replacements, we're only allowed to go up to 35%. And even that's a little bit of a farce based on the specific mix design, because there's also a minimum cement requirement. So we thought we'd kind of look at that and understand if we try to push the boundaries almost to maybe not failure is the right word, but just really push the boundaries and figure out what does it look like in terms of set time performance, not only in the plastic properties, but also in the hardened state. And because of that 50% limitation placed on F3 exposure classes, for anything over that 50% limit, we reduced the water cement ratio, which was dictated by the IDOT spec at a 0.42 down to a 0.40, just to kind of help enhance the potential durability characteristics. And then also explore what does that look like in terms of workability, right? I mean, obviously we know as we go up higher replacements of slag, due to the angularity, there may be a little bit more water demand. So if we do that, not going too far, down to a 3.5 or 3.6 or something like that, what does that look like in terms of actual concrete that we can place and that our contractors feel comfortable with? So what we did is, again, we took the 35%, as I said, it's, relatively around there. And then we did the 50%, which was limited by ACI, and then did 60 and 80%. Really trying to understand what does the strength gain curves look like, and, what can we expect out of that? And, as fairly expected, really no issues hitting strength. I mean, an IDOT spec is 3,500 PSI in 14 days for that particular class of mix that we looked at. So that's really not necessarily an issue, as we tested, at 3, 7, 14, 28, and 56. And I think also looking at the 80%, obviously that's really pushing the boundaries a little bit. But I think if we would have carried that out to a 90-day strength curve, I think you would start to see it, closer to that, between 7,000 and 8,000 PSI, just as it takes a little bit longer to get there. So, I think as we all would kind of assume, the strength really wasn't necessarily as much of an issue. But again, had to check that box to make sure that, those higher replacement rates weren't going to put us in jeopardy of not meeting the specification. And then obviously set time, always a very important characteristic when you start to look at, mixes with higher replacement rates. Not only from a GWP reduction standpoint, but just from the contractor schedule, finishability, getting the finish on there that they need, getting the curing compound on there. And so, as you can see, set times are all relatively close. The drop in water cement ratio on the 60 and 80% mixes, I think did help bring those in line. I would have anticipated those to be higher if we left them at the 0.42, but at first blush, I think that got us pretty close to where we needed to be. So again, just trying to really manage the expectations and check the boxes that are important for not only, constructability, delivering the concrete and getting it on the ground and getting the finish that they really need to get on there. And then the big one, right? The big one that is a concern of, anything 50% and above is looking at the freeze thaw through ASTM C666. While not the biggest fan of this particular test, it is required in a lot of DOTs and other performance specifications. So trying to understand what does that look like. And while you do see some of the RDM values drop a little bit as you go along, I think that allows for an opportunity to look at some of these new emerging admixtures that are out there, whether it's internal cures, internal sealers, different potential methods of curing. I think there's some opportunity there to to take some of these mixes that, you know, may not have the freeze-thaw durability based on this specific test, to get them closer to that 90-95%. But I think there's definitely an opportunity there. And, you know, and I realize that C672, the salt scaling resistance, was pulled, but I think that is also, you know, a test we still like to run to understand really what is the surface doing. That's really where we start to see a lot of inquiries and people concerned about, if I go to this level of replacement, what is that going to do to the surface, right? Everybody wants it to look nice and look pretty. And, you know, I would agree that, that's part of our job to make sure that we can do that. So, again, just understanding what this does, and then how do we kind of take it to the next level and confirm that we can produce a concrete that has higher replacement rates than what ACI says at this point in time, and still have a long-term durable product. And then looking at bulk resistivity, again, another durability test, you know, as expected, measuring it at 14 and 28 days across the varying replacement rates. We see that the chloride penetration got better and better. So there's a higher chance of that particular mix not bringing those chlorides in that would do the damage that maybe the C666 method showed. So again, trending in the right direction here. And I think if, you know, again, mentioning, looking at some of those new admixtures that are out there, I think we could even start to see better numbers here as well. So again, trending in the right direction. Again, another durability characteristic, dry and shrinkage, C157. As you can see, is again, I think as we would all expect, the higher replacement rates had great shrinkage numbers. The 60% there is a little bit of a flyer, again, just one data point here, but again, all good shrinkage numbers that would prevent these mixes from cracking and allowing the ingress of salts or de-icing chemicals that would eventually, you know, get through the concrete and damage the reinforcement that's in there. So again, still trending in the right direction, thinking that there's definitely some opportunity here to continue exploring what these mixes can really do if we started to push the boundaries of the replacement rates. And so realistically, you know, this the sheet from the Slag Cement Association here, kind of looking at typical ranges of slag cement that was used, you know, and looking at applications, like I said, where it makes sense to really maybe push those boundaries, where footings, foundations, you know, pushing at 40-50%, not really too much of an effect on, you know, overall schedule or you know, relying on a set time there. Because realistically, average, you know, around the industry, or at least, you know, from what we've seen, is around 16%, whether it be fly ash or slag. So I think there is a lot of opportunity there to continue to push the boundaries. And, you know, again, as we get into it here shortly, the reduction in carbon by replacing slag cement as a 1-for-1 for, you know, Portland cement, you know, in your area, if it's a type 1-2 still, or even the PLC cements, there's going to be an opportunity there. So I think understanding that, you know, there are applications where we can really push the boundaries and, you know, take advantage of a little bit higher replacement. And I think it's very important to also, you know, each region is different. You're going to have different materials, different aggregates. You know, the cements react differently with the slag. So understanding how it all works within your region, I think, is important. And, you know, being able to, again, communicate what, if any, differences there would be from a particular mix that a contractor is used to. So, you know, I think this guide here is very good. It allows you to kind of look at, you know, different applications and understand, you know, where we can maybe, you know, increase the percentage a little bit without really having too much of an effect on the overall project. And so really getting into the global warming potential, right? So within an EPD, you're assigned a global warming potential, which is the kilograms of CO2 per ton of material when it comes to cementitious products, or per yard or cubic meter of concrete. And the Portland Cement Association put together the industry-wide PLC cement number. So for that, which includes all the domestic sources of cement, as well as all the import sources of cement that come into the United States, it's around 846 kilograms per ton. Slag Cement Association did the same thing for all domestically produced slag as well as imported slag, and that comes in at about 147. So as you can see, a pretty substantial reduction there. So just by replacing slag with, or replacing Portland with slag, you're getting an overall reduction. And then, a lot of producers have taken it one step further and gotten product-specific EPDs. So they look at a specific location, whether it be a cement mill or a specific grinding plant, and determine really what is their true global warming potential for that product from that location before it leaves the gate. And just looking at a specific slag source here, right in the Chicagoland market area, is 95. So again, understanding really truly what your materials are. And, I think the industry has done a really great job at getting their product specific EPDs, because, while the industry-wide ones are a great starting point, in trying to eventually get to zero, you really need to know where you're starting at. So again, we're still in this little bit of a carbon accounting phase, but the more accurate information you have, the more, higher level of accuracy your EPD is going to be for your particular mix design. So, as you can imagine, increasing rates of slag cement do ultimately overall help in reducing the carbon footprint of that yard of concrete. It's kind of circling back again to those mixes that we did, looking at the IDOT pavement mix, understanding that, this is, global warming potential in kilograms of CO2 per yard, starts at about 160, for our particular region, and goes down to slightly above 80. So almost nearly cutting it, in half. But as you can see, the replacement rates of slag will have a significant impact on the global warming potential, and less of an impact on the performance and durability, as we saw in those subsequent slides. Whereas looking at fly ash or natural pozzolan or some other SCMs that maybe are a little less reactive, I think you're going to see more durability or, even finishability constraints placed on that. So again, slag is from our perspective, is a great product to help reduce the global warming potential while not having as great of an impact on the mix designs and the performance that they have when it comes to the contractors and the placement and the workability. And then I kind of wanted to take a look at just some pilots and some at-scale applications that we've done within our market. We started to slowly start to see the increased demand for meeting carbon reduction goals on projects, and whether it was them just looking at alternatives, or whether they had a specific target goal of by mix design, right? Some specifications will say not to exceed a certain GWP for this application. Some will say we want an overall project reduction of 30%. And 30% from what, right? Some have their own internal baselines from previous projects that they've worked on. Some are using the NRMCA baselines. Some are using the NRMCA baselines with a percent reduction off of that. So, obviously, as you endeavor into some of these projects, you need to understand what the goals are and really what are they trying to achieve, whether it's on a per mix basis, which can be a little bit more restrictive and challenging, because obviously there's some particular applications that are going to be a little bit more critical path, if you will, or have higher restrictions in terms of performance or end characteristics of the particular application. So really understanding, how do you look at some of these applications and figure out what's the best one to tackle, right? How do we kind of dip our toe in the water, get comfortable with this? Because it's not just from a producer standpoint making new mix designs, right? In theory, that's kind of the easy part, right? But getting the rest of the project team on the same page as you, and understanding that, all right, say for this particular application, call it the footings or foundations, right? Not as much of a big impact to the schedule, not a lot of risk tolerance, to say if it was an exterior slab on grade, we're going to do higher than what ACI recommends, right? And again, understanding if we do go this route, what should we expect, right? How do we get, whether, with being the owner, to understand what potential risks are they willing to take on, right? If maybe there was a little bit slower setting and there was a small premium assigned to the schedule, or you had to throw some additional accelerators or admixtures in there to make it work, right? Are you okay with that? Understanding that, if we did go to a higher replacement on an exterior pavement or even an interior slab, if they couldn't saw cut in the timely fashion. You know, if there is a small shrinkage crack, is that okay, or is that a non-starter? So, you know, being upfront and honest is, you know, what we have found has been the most crucial piece of this, because we can get anybody a mix and say, you know, yeah, it'll make strength, but that's only one piece of it. So, you know, having these conversations early on and often throughout the process, especially if they're trying to, you know, go above and beyond what they normally have done, is really important. Because the last thing we want to do is try and promote, you know, sustainable concrete with higher replacements with slag cement and fall on our face, right? I mean, that just gives, you know, the industry will quickly catch wind of that, and it will just give a black eye to, you know, low carbon concrete, because it's not necessarily bad. It's just different. You know, as my last point here is, you know, there's a lot of people that automatically assume that just because it's low carbon, that it's going to, you know, lay there for 3 days, or it's going to, you know, take forever to get strength, or, you know, they won't be able to place it or finish it. So again, understanding your materials and your mixes, you know, the replacement rate you're looking at, you know, don't be afraid to do trial batches on your own, not even necessarily for this particular project or on the project, but do them internally, understand what you're working with. And again, managing the expectations of all the players involved, from, you know, the concrete contractor to the general contractor to the owner to even the testing company, right? The testing companies need to understand that, you know, the mixes of the past, you know, even just a year or two ago, using type 1-2 cement with, you know, 15-20% slag, you know, they had a lot of forgiveness in them. You could potentially maybe not put them in the cooler or store them per ASTM. But, you know, these mixes now using PLC cements with higher replacements of slag, they're more sensitive to temperature. They really need to understand that them following the methods of proper curing, managing the cylinders and handling the cylinders is going to become all that much more important as we continue to go down this path, because a difference of 4 or 5 degrees could make the difference of whether it makes strength or not. And you're dealing with low strength, you know, low strength phone calls and coring or non-destructive testing, and, you know, additional costs and project slowdown. So, you know, again, getting, you know, and I don't mean to sound like a broken record, but having more than normal conversations with all the players at hand, it needs to happen until this becomes the new norm. And, you know, as we continue to try to get to net zero, these mixes are going to become less and less forgiving when it comes to the testing criteria and how they're managing the cylinders and casting the specimens. So one particular application, again, you know, we felt that foundations and footings are a great application to really start to push the boundaries of slag replacement. So this was a data center we recently worked on. There was a 4,500 PSI with air requirement for these foundations. And as you can see, they're fairly large in scale. So they had the requirement, they needed to strip those forms in one day to keep moving. Otherwise, it was going to start to affect the schedule. So we did a trial or two internally and got comfortable with the early strengths, communicated with the contractor that said, hey, is this going to work for you? You know, at 24 hours, we're at X PSI. Are you going to continue to move on, or do we need to make some tweaks or adjustments to this mix design, whether it's water cement ratio or maybe a slightly lower replacement rate? But based on the information we provided them, you know, they were able to make this happen. And now, granted, when it got into some colder temperatures, as you experienced in the Midwest, you know, they did have to put a little bit of accelerators in there, which is not that uncommon. And again, you know, the notion of a premium for a green mix is, you know, when you're looking at additional admixtures, is pretty nominal. So again, you know, we did 20,000 plus yards with this, with great success. The testing company was on board, knowing that they had to cure these, you know, properly in the right way. And it was a 33% reduction in CO2 from the NRMCA baseline for this particular region. I particularly like to use the regional numbers as opposed to the nationwide numbers. It's a little bit more specific to our particular area and with the materials that we have available here, and the cements and the aggregates. So that's my personal preference. But again, a lot of projects will have particular baselines that they want you to follow. So, you know, again, these reductions can be a little bit of you know, a moving target, if you will. You know, it may be a 38% reduction from another baseline. It may be a 25% reduction from somebody else's baseline. But just understanding what baseline you're working from, and being able to calculate the EPDs to give them that information allows the owner and the general contractors to make the informed decision whether they want to proceed with this particular mix design, and if they're willing to accept, potential hiccups here and there, because again, not bad, but different. And with that just comes a little bit of a learning curve. So, and really the only way that's going to happen is to continually put this on the ground and understand the different variables that you're going to encounter with it. Another one was a hydroelectric dam we did for Notre Dame. They had a renewed commitment to cut their emissions in half by 2030. And so when this project came out, we really looked at the specifications and understood it was going to be a little bit more complex of a project based on it being mass concrete and being pumped underground, underwater. And so we really felt that slag was the best viable solution for us. And, we were able to, hit their 8,000 PSI requirement, pumping at 50 feet underground with a max temperature set at 160, which we never came close to. And, we placed 7,000 plus yards with an 80% slag replacement mix. And again, a 55% reduction from the baseline there. So, again, the flexibility of slag to help meet not only a high strength requirement, but still the pumpability, which everybody needs and wants. And, for this particular application, the thermal control plan, slag was basically a no-brainer. And again, ultimately gave us the strength that we needed and complemented that with the CO2 reduction that the owner was looking for. So it was really a win-win-win for all the parties. And the contractor was fully on board, understood what we were doing, and was very pleased with the way the mix placed, pumped, and went through the forms. And so again, just understanding what the requirements are and figuring out how do we help achieve the goals that everybody needs from the top down. And then another at scale application. I know again, as you see in the notes here, 20% slag replacement, not that crazy, but when it comes to warehouse slabs, at least in this particular market, it's a very critical path item, very sensitive to FF and FL requirements. And again, the set time, right? I mean, the labor is a huge piece here. So, we did a little pre-work on our end and, looked at our normal warehouse slab mix, which was typically a straight bag mix, and looked at varying replacement rates of slag from 10 to 20 to 30%, and figured out, okay, if we want to help achieve what the contractor wants, the largest piece of a typical warehouse is the interior slab, which will drive labor costs the most. So how do we give them the information that they need to feel confident in bidding the project with a reduction in CO2 by replacing cement and still deliver at the end? And so we did some work ahead of time, figured out at what dosage rates of NCA at some varying temperatures they would need to use. And the project went off without a hitch. We were able to give them obviously the strength, usually never an issue here, but their FF and FL numbers are great. They actually commented that the mix finished better than straight bag, which was, always a good thing, right? In our industry, you don't get too many compliments, but when they come back and say that it finished better than what they're normally used to, didn't cost them any more time. Again, the small incremental costs for accelerators, they weren't crazy. In the grand scheme of things, it was single-digit percentages, and we were able to get a 22% reduction from the NRMC baseline. So, starting to dip your toe in the water in some of these applications, especially as you see some of these larger facilities going up, where they've got 40, 50% reductions from baselines, pushing the limits on replacement and the footings and foundations is only going to get you so far. So we really think that looking at these large interior slabs is going to be a crucial piece moving forward to help these owners really get to those higher replacement amount or higher reduction amounts that they're looking for. And again, working with the contractors hand in hand, understanding what are their concerns and how do we address them, and how do we make everybody feel comfortable going into this, that they can still deliver a quality product at a low carbon number. So again, just to reiterate, I think, the most important piece to a lot of these carbon reduction movements in any application, any project, is getting involved early on before the specs are baked. I mean, if the contractors are coming to you and saying, hey, I need you to bid this project, here's the specs, it's almost too late, right? It's difficult to go back and look at some of these things, but getting involved early on, and understanding what are the capabilities of the producer, what materials are available in that region. You know, maybe it's just an ash market, or maybe you have slag and ash, or maybe it's just slag. So understanding that, you know, with slag, you do have a little bit more flexibility in increasing those rates without having as much of an impact on performance. So I would encourage everybody to be comfortable with that. You know, don't hesitate to try to just do some trials in your facilities. Understand that when you start to go up to 40, 50%, what does that look like with your materials? What does that look like at a 3,000 PSI mix versus a 8,000 PSI mix, right? You know, as the amount of Portland changes, the strength curve is going to change. The sensitivity to curing is going to change. So really understanding those and being able to effectively communicate those to all the stakeholders within a project is only going to make it more successful. You know, don't be afraid to tell them that, hey, this may be a little bit slower, but we're going to work with you to figure it out. Or you may experience X, Y, and Z, but this is what we think will help you. So, you know, trying to just pitch a 50% slag mix, the same as a 10 or 15% slag mix, I think would do it a disservice. And, you know, understanding all the stakeholders, you know, tolerances for risk, for what are their, you know, their major concerns or critical path items that they need to achieve. You know, again, gives you the information that you need to help design properly and at the right rates for the right application. So with that, I thank you for the opportunity and would welcome any questions.
Thank you, Ryan. We have a few questions lined up here. The first one is, agree that C672 and C666 should be run when exposing to freezing and thawing. Should the C666 testing allow for additional curing time at high replacement rates?
Yeah, I would agree. And I think, you know, I've had this conversation with a lot of different people that I think as we continue to go down the low carbon route with less and less clinker, I think curing practices need to be looked at differently. And even just the standard testing procedures that we've been doing for decades now need to be looked at differently. You know, it doesn't necessarily mean that a mix at 60 or 70% slag is bad for freeze thaw, but maybe understanding that maybe there might be some more limitations on when you can really place them. You know, if you're bordering up upon, you know, within 30 days it might freeze, is that acceptable? Is that okay? Or should we take additional protective measures for that particular slab? You know, I think that's definitely something that needs to be considered moving forward, not only from, you know, just, you know, 666, but even just, again, testing or curing in general for cylinders, because, you know, what you're capturing in a 4x8 or 6x12 cylinder, you know, maybe a couple of degrees different than really what's happening in situ of that concrete, and the lower clinker factors, those couple degrees could mean a big difference.
Perfect. Our next question is, for the testing data that you showed, which cement version did you utilize?
We used at the time, I mean, our market switched over to all Portland limestone cements probably about a year and a half ago. So we used a PLC cement with just our local grade 100 slag.
Our next question is 4,500 PSI for 28 day, but what was required for the 24-hour form removal?
Well, I think it was like 1,200 PSI or something like that they needed to strip the forms without any, you know, peeling or anything on them. So yeah, the 1,200 PSI was not an issue for that particular situation. And again, I think that's going to vary depending on each project, right? Depending on the size of the forms, the thickness of the member, things like that. So each one's going to be a little bit unique. So, you know, I would encourage just having that conversation with the contractor to understand, you know, what do they need and how do we help achieve that goal for them.
Perfect. Then last question we have right here is, what is motivating customers to ask for slag cement? Is this for environmental benefits? Is this the government or owners asking for it, lower cost, or something else?
You know, I wouldn't specifically say they're asking strictly for slag cement. I think what they're asking for is a carbon reduction to some degree. And with that, you need to look at within your environment, or within your region, what's available, right? And, for us, we do have a good amount of slag here in our market, so we're very fortunate. So for us, utilizing slag to get to lower GWP numbers has less of an impact in terms of the performance and how the concrete's going to behave differently than what they're used to. So that's one reason. And again, yeah, a lot of it is driven by owner requirements per se, just on the carbon reduction. We haven't, there's definitely legislation in place in some states, not necessarily in our markets yet. But I do think that's going to be coming down the pipeline. I think more and more governmental agencies, obviously GSA has their own specific requirements, but when it comes to municipalities and state DOTs, I think they're going to start to have more, I don't say restrictions, but encouraging people to design lower carbon mixes when it comes to concrete. And its cost is a very market dependent situation, and can be a a loaded question at times.
So we got a couple more questions in. What is the best approach for enhancing early mechanical performance when slag partially substitutes cement?
I think, again, looking at the design itself and understanding the water cement ratio, right? I mean, obviously, as you go down in water cement ratio, mixes become a little more difficult to challenge, but I think there's been some great advancements in admixtures in the last couple of years that have been targeting this particular situation, right? Obviously, as the lower water cement ratio gets, you get the better early strengths, the better early performance that people are typically used to with a type 1-2 cement in a call it a 15% replacement. So again, understanding your local materials is going to be crucial in this because, some you may be able to drive the water down, some you may not be. And if you can't, then maybe you need to look at some strength enhancing admixtures, or, if you can drive down the water a little bit, look at some of these new advancements in polycarboxylates in terms of workability, slump retention, things like that. So, I would encourage people to engage with their admixture suppliers because there are a lot more resources out there than there were 5 or 6 years ago. So it gives you a little bit more flexibility. But, again, it's managing that threshold of, you need a certain amount of water. Everybody knows that. And if you go too low, you're fighting an uphill battle in terms of a mix that's going to be workable, right? You might get the strength that you need. That's, usually never the issue, but how do I get it off, out of my plant to the truck, to the job site, into the forms or into the placement they want and get the finish on there or whatever it may be. So, a lot of different variables you got to consider, and that will vary depending on the application and your materials.
Perfect. And our last question here is there much work or research being done with varying slag use of concrete mix designs for precast?
We particularly are not in the precast industry, but I have heard from some owners that we've dealt with here recently that, yeah, to them, the precast industry is again a little bit of a holdout for them. Obviously, from my limited knowledge on precast, obviously for them is turning their beds is kind of their business model, and obviously slower strength gain and potentially slower set times, is a bit of a disruptor. So I do think that is an area that can be looked at. And again, I think there's admixtures that could probably help you get there, and potentially looking at, different strategies, whether it's maybe applying heat or things like that to help them drop their global warming potential for their members. Because I know, like I said, it's been a bit of a struggle for some larger owners that are looking, that's kind of one of their last pieces of the puzzle is they're not getting a lot of buy-in there. So I think there's definitely an opportunity there for somebody to differentiate themselves and say, hey, listen, I can offer you a low carbon precast application or for this tilt up wall or whatever it may be. So, I think that's definitely something that should be explored further.
Perfect. Looks like we got one more question. I think I can answer this one. Can you say anything about regional or future availability of slag? So, a few of our SCA members have recently announced expansions of their plants and conversions of their facilities into slag grinding facilities. So, yeah, we do expect growth there of slag domestically in the United States. So, look forward to that. Those are all of our questions I've received so far. If you have any additional questions for Ryan or I, you can contact us at info@slagcement.com. slag.org, and we can answer those questions there for you. This webinar will be available on demand on SCA's YouTube channel and on our website, so you can watch it there as well. With that, I want to once again thank Ryan for speaking today, and I want to thank all of you for attending. Really appreciate your participation in this webinar. Thank you.
Thank you.